Okay, we're back. So, I think before we head to lunch, I'd like to get through metabolic. Before lunch, I'd like to get through metabolic alkalosis, and we'll talk about that. And then after lunch, metabolic acidosis, and that's where a lot of the nuance from our perspective is going to come from. So let's talk about metabolic alkalosis. Metabolic alkalosis. So with metabolic alkalosis, it really comes down to two major types or two major causes of metabolic alkalosis. The first major cause is a loss of hydrogen ions. So you have an excessive loss of hydrogen ions that can cause you to become more alkalotic. And then the other major cause is simply retaining too much bicarbonate. Right, so I'm either losing too many hydrogen ions, or I'm retaining too much bicarbonate. These are kind of the two major ways that we can do it. So let's talk about loss of hydrogen ions first. And this can occur in a couple of different ways. The first major way that we can lose too much hydrogen ions is through the gastrointestinal tract. So I can have GI losses. All right. And two things that you want to be thinking about: vomiting and gastric suctioning. Right, so somebody is vomiting excessively, or they have a gastric tube, a nasogastric tube, or oral gastric tube, or some other gastric tube place that is continuously suctioning the stomach. Well, what's happening? Well, what do you have a lot? What do you have in your stomach?
A lot of acid.
You have a lot of acid, right? Hydrochloric acid. So if you're suctioning more of that out, you're losing all of those hydrogen ions. Does that kind of make sense there? And so that is a way that a fairly common way that you can develop metabolic alkalosis is just simply by either vomiting excessively or suctioning the stomach out excessively. Does that make sense? Hopefully that kind of makes sense there. And so a general rule of thumb that you want to think of is you tend to lose acid out of the mouth, all right, and you tend to lose base out of the butt, all right. So if I have excessive diarrhea, for example, I tend to lose a lot of base, which means I tend to develop acidosis, right? Metabolic acidosis, not alkalosis. Okay, so that's one major area where we can have an excessive loss of hydrogen ions. The second major area is through the kidneys, the renal. You can have a renal loss. Renal loss of hydrogen ions, and there are many different conditions that can cause this, all right? So some things that you want to think about: diuretics. Putting somebody on diuretics and low sodium diets. All right, so diuretics and low sodium diets. Hypochloremia. Hypochloremia. Decreased chloride concentration, right? Hypokalemia, or decreased potassium. Hypovolemia, right? Decreased fluid volume. So all of these, some of these, or a combination of these, can cause renal loss of hydrogen ions. And it's really complicated what's going on there. It's actually fairly complicated, and we'll talk about it in a little more detail in renal when we talk about renal and genital urinary emergencies. But essentially what happens is you have lots of different pumps within the nephrons of your kidneys, and these pumps are ion exchange pumps. They exchange sodium with hydrogen ions, chloride with potassium ions. There are these different exchange pumps. And so what can happen is if I become, say, hypochloremic or hypokalemic, right, I'm not able to as effectively move these ions, and that can lead to an excessive loss of hydrogen ions because there is an exchange that occurs, and then other pumps have to take over, and kind of some other things can happen. We don't need to go into the minutia of all that at this point, but that's kind of what's going on. So I'll give you maybe one example of this, and let's take a common example of excessive vomiting or gastric suctioning. So you remember that picture that I put up earlier of the red blood cell? All right, so what I'm going to do is I'm just going to draw you a little picture here of not the red blood cell, but I'm going to draw you a picture of the blood stream here. So this is the blood, we'll say. All right. And then I'm going to draw a gastric cell here. So this is a gastric cell. And then this here is the inside of the stomach. We'll put that in a different color for you. All right, something like this. Okay, so what do we have in the stomach? What kind of acid? What is this specific acid?
HCl.
Hydrochloric acid, right? So I have HCl in the stomach. So the question is, and of course the HCl dissociates into hydrogen ions and chloride ions irreversibly. Okay, so the question is, how do I get hydrochloric acid, right? How do I make it? Well, first of all, you have a lot of chloride in your blood, right? I have a lot of chloride in our blood. So what happens in your gastric cells is something very similar to what happens in the red blood cells, right? So you have CO2, right? And CO2 plus H2O gives us what? H2CO3, right? Carbonic acid. And then what happens to the H2CO3? It breaks down into hydrogen ions and bicarbonate ions, HCO3 minus. All right, you okay with that? So what happens is this hydrogen ion that's produced from this chemical reaction is taken away. All right, and then the bicarbonate, and what charge does the bicarb have on it? As a negative charge. So the bicarbonate is then sent into the blood. And if I put a negatively charged ion into the blood, what has to happen in response to that? A negative has to come out to maintain electroneutrality. Does that make sense? So as the bicarb goes into the blood, what's happening to the bicarb level in the blood? It's increasing, right? I'm going to take chloride out of the blood, and then that chloride is going to go into the cell here. So here I have chloride, and here I have those hydrogen ions, and then the hydrogen can combine with the chloride to make hydrochloric acid, which is then released into the stomach, right? So that's how we make hydrochloric acid, but now the question is, what happens if I start vomiting? What am I losing? I'm losing all this hydrochloric acid, right? Does that make sense? So what do the cells have to do? Your gastric cells have to make more hydrochloric acid, which means more carbonic acid's produced, more hydrogen ions, but what's happening? Those hydrogen ions, are they staying within the body? The hydrogen ions are leaving, but what's staying behind? the bicarbonate, right? Because the bicarbonate's going into the blood and the chloride's leaving the blood, right? And so what's happening to the bicarbonate content within the blood? You're increasing it while at the same time eliminating hydrogen ions. Does that make sense what's happening there? So this is just one example of the pathophysiology behind metabolic alkalosis, and you can see it's kind of complicated, isn't it? There's a lot going on. That's one example. I don't want to get into the renal stuff so much, although I will a little bit this afternoon. It's kind of unavoidable to some extent. Okay, so that's one way you can get there. The other way is by retaining bicarbonate ions, right? So how can I retain bicarbonate ions? Well, what if I give somebody bicarbonate? Right? What if I give them bicarbonate infusions? So I administer bicarbonate, too much bicarbonate to somebody. Might that cause metabolic alkalosis? Absolutely, yeah. What if my patient ingests? What if they ingest alkaline? Right? Alkalotic solutions, right? So maybe they ingest something that has high bicarbonate concentrations. Might that get you there as well? What do you think? Yeah, absolutely. Absolutely. Yeah. Absolutely. Absolutely. I'm just going to put a little asterisk here. And again, I don't want to go into the minutia of it, but what I want you to remember over here is I want you to remember that the kidney must secrete. So when I'm secreting something, what am I doing? I am holding on to it or getting rid of it? Getting rid of it. So the kidneys secrete something, that means it's going into the urine and they're getting rid of it, right? So kidneys, what they need to do is they need to secrete hydrogen ions in order to reabsorb sodium. And what's reabsorption? If I'm reabsorbing something, what does that mean? I'm pulling it back in, right? And it's staying within the blood. That's reabsorption, right? So in order to reabsorb sodium, right, one of the ways that the kidneys can do that is they can secrete hydrogen ions. And that maintains electroneutrality. I'm holding on to sodium, I'm getting rid of a hydrogen ion, right? I'm exchanging those two. Does that make sense? Now that's not primarily what happens. We can exchange sodium with other ions, right? I can hold on to sodium and I can get rid of potassium, for example, right? However, if I have hypokalemia or hypochloremia, the primary ways in which I can exchange those ions are altered, and so what I have to do, or what the kidneys do, is they secrete hydrogen ions in order to hold on to sodium if chloride levels are low, potassium levels are low, or the fluid volume status is low. If these are, or one of them is low. Right? Does that make sense? Without getting too detailed there? Okay. So when somebody develops metabolic alkalosis, and you see this on the ABG as a primary problem, because metabolic alkalosis might also be a compensatory mechanism, they might be compensating for respiratory acidosis. But as a primary problem, metabolic alkalosis is a primary problem, right? These are the things you want to think about: vomiting, gastric suctioning, diuretics. hypochloremia, hypokalemia, hypovolemia, and excessive intake of alkaline solutions. You guys okay with that? Now I want to briefly talk about alkaline solutions, because sodium bicarbonate is a medication that we can administer, right? And in the past, we would actually administer sodium bicarbonate to patients who were acidotic. Well, that makes sense. If they're acidotic, why don't I give them base, right? Does that make sense? Seems legit, right? Let's talk about why that might be.
You would still have, just because you're giving them more base doesn't mean they're getting rid of the acid, right?
Well, you can buffer that acid, so you might change the pH. Maybe if I give them base, maybe.
Isn't it? So it's a buffer. So basically, it's going to take a lot longer for your body to recreate whatever it needs, right? Since it is a buffer.
Well, it will take longer for the body to make it than it will take for you to inject
or
it
to
into the
actually
body.
change the pH. Like if you gave someone too much sodium bicarb, right?
Well, their pH might change. Might being the key word. The question is, well, let me show you guys something. So let's go back to carbon dioxide. So what happens to CO2 when it's produced? It is combined with what? Water. CO2 plus H2O. And remember, I'm drawing arrows in both directions, right? This is going to be important. So CO2 plus H2O gives us H2CO3. That's carbonic acid. And then that can give us H plus and HCO3 minus. And then that can give us, I can recombine, right, to form what? H2CO3. And then that breaks down in the lungs to form H2O and CO2. You guys okay with that there? And this tends to happen in the tissues. And this tends to happen in the alveoli. All right. So, see these arrows here, right? These arrows means that this chemical reaction can occur in this direction as well as this direction. Okay? This is a reversible or an equilibrium reaction. Now, we haven't talked about this yet, but there's a principle in chemistry called the Le Chatelier's principle, or du principe Le Chatelier. All right? Le Chatelier's principle says that in a chemical reaction like this, that can go either direction, if I increase the value of something on one end, so if I increase the value of something on this end, it will shift the chemical reaction in the opposite direction, because the chemical reaction is trying to obtain equilibrium, right? Now, normally, what direction does this chemical reaction go in? Good, because you have carbon dioxide constantly being produced, right? And so as CO2 levels increase, that's going to shift the chemical reaction in this direction, right? Does that make sense? Okay. So here's a question. If I give somebody a large dose of sodium bicarbonate, NaHCO3, what happens to that sodium bicarbonate when it enters the bloodstream? It dissociates into sodium ions and bicarbonate ions. Okay, so check this out. If I give somebody a large dose of sodium bicarbonate, what element of this equation am I increasing? Am I increasing it here? 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 Yeah, right? So I'm increasing bicarbonate here. what that can do is that can shift the chemical equation to the left instead of the right. If I add a bunch of bicarbonate, that can shift this equation to the left, and it can cause increased CO2 production in the body. Well, that's kind of a problem potentially, right? That's particularly a problem in what kind of patient? So if I give them, does that make sense how? If I give somebody a large dose of sodium bicarb, how that can increase their CO2 level, right? Even though CO2, you can't get CO2 from bicarb, it shifts this equation to the left, right? Right, because this doesn't care. This equation doesn't care if it goes right or left. It's all about maintaining an equilibrium, right? Normally, it's going to go left because you're always making CO2, and so it's going to push that equation in this direction. But if I dump a bunch of bicarb on board, I could shift it to the left instead of right, and that will make more CO2 in the blood, right? Well, what kinds of patients could this be really problematic with? Yes. If you give sodium bicarbonate to someone who is not adequately ventilating, this could be a big problem. This could be a really big problem, right? So you're going to create lots of CO2. They won't be able to eliminate that CO2, and potentially it could even make an underlying acidosis worse because of that CO2 retention. Does that kind of make sense? So if your patient is not ventilating adequately, and you cannot ventilate them adequately, it is not recommended that we give bicarbonate to that patient, right? So what kinds of patients would not particularly benefit from bicarbonate therapy?
It's like COPD.
Maybe COPD patients would be a bad deal. Okay, if they have a substantial respiratory acidosis, not a great idea.
What about anaphylaxis?
Maybe anaphylaxis. What about cardiac arrest? What if you're in cardiac arrest?
Yeah, because you're more retaining.
Yeah, you're not ventilating very well in cardiac arrest, are you? Yeah, you're not breathing. And even if you're ventilating somebody, there's no guarantee the lungs are being perfused very well, right? And this is interesting because back in the day, when I first learned advanced cardiac life support, we gave patients in cardiac arrest bicarbonate, right? Oh, well, they're acidotic. Why? Because they develop lactic acidosis, right? And so we give them bicarbonate, right? Well, clearly that's probably not the greatest thing for somebody in cardiac arrest, right? Because we're not necessarily effectively eliminating the CO2 because it might not be getting to the lungs, because the lungs might not be being perfused very well. Yeah. So you want to be very, very cautious about giving sodium bicarbonate to patients who are not effectively ventilating, i.e. cardiac arrest patients. There obviously are some caveats to that, right? If that cardiac arrest is, say, due to tricyclic antidepressant overdose, well, what's one of the major antidotes for tricyclic antidepressant overdose? Sodium bicarbonate, right, to increase their sodium load. In that case, clearly the bicarb, right, the benefits would outweigh the risks. Or what if that cardiac arrest was due to life-threatening hyperkalemia? Well, what's one of the things that bicarbonate can do? It can shift potassium ions into the cells, right? So the benefits may outweigh the risks, but you're working a cardiac arrest and somebody runs ABG. Oh, this patient has metabolic acidosis, so let's give them 2 amps of bicarb. Whoa, hold on. Why do you want to do that? And maybe there's a good reason. Oh, well, this is a dialysis patient and we're worried about potassium. Oh, okay. Well, because the pH is low, you're going to need a little more than that to justify. Does that kind of make sense there? Okay. So anyway, I thought this would be a good point to have that discussion about bicarbonate and about Le Chatelier's principle. Okay, Let's see, we're rapidly moving toward 11:30, which means lunch is approaching.